In this video, I want to take a look at the relationship between the eigenvalues of a matrix and the determinant of that matrix. And, well, here's that relationship. Theorem: if A is an n by n matrix, then the determinant of A is equal to the product of all of the eigenvalues. Now that takes into account multiplicity. So if a particular number is an eigenvalue with multiplicity 3, then you have to include it in the product 3 times. And here's the proof. So to find eigenvalues, we solve the equation. The determinant of a minus lambda I is equal to 0, and any such lambda would be an eigenvalue. Right? Now the book does it lambda I minus a, whatever, multiply both sides of this equation by minus 1, and the solutions are the same. Okay, so here's some things to notice about this equation. One, the determinant of a minus lambda I is equal to this polynomial, right? That is, when you multiply it all out, you're going to get an nth degree polynomial. Now, a couple of things. The an here is either plus 1 or minus 1, and it's plus 1 if n is even, and it's minus 1 if n is odd. Now, the way the book would do it, they would do the lambda I minus a, and for them, the an would always be plus 1, because all of these lambdas would have a plus in front of them. Okay. Now, I do it this way because I don't care whether that's a plus or minus 1. What I care about is the a0. So here we go. If r is an eigenvalue of a, then r was a solution for lambda, which made this equation true, which means if you plugged that value of r into this polynomial, then it would be a 0 of the polynomial, which means r minus lambda is a factor. Typically, we would say lambda minus r is a factor, but if lambda minus r is a factor, then so is r minus lambda. It's just with an extra factor minus 1, right, if you need it. I'm writing it this way because of the way that I do it, a minus lambda I. My lambdas are on the right side of these polynomials. So I know that factors and eigenvalues go together, right? If I have a factor, then I get an eigenvalue, or if I have an eigenvalue, it came from a factor. Now, with what do I have next? The determinant we already said was equal to this polynomial, but the fundamental theorem of algebra implies that every polynomial can be factored into linear factors. Now, it's possible that in order to do that, you needed to use complex numbers for these coefficients in here. Now, I know that these are all they're all minus 1s because each of these r minus lambdas have to be factors. And there isn't any extra factor. Sometimes you can say, yeah, it's r minus lambda is a factor, but then you have to multiply by 3 in the end because the coefficient in front of the highest power of n, or whatever your variable is, the nth power of lambda, is not 1, or it's not minus 1, right? But here I know it is 1 or minus 1, and so all these factors, these r minus lambdas, or r1 minus lambda, r2 minus lambda for all the different eigenvalues, they're all factors, and when you multiply this out, the coefficient from the lambda to the n is going to be either plus 1 if you've got n negative sign, if an even number of negative signs, and it's going to be minus 1 if you've got an odd number of negative signs there in front of the lambdas. So this is how it factors, with all of those eigenvalues being the constants in each one of those terms, in each one of those factors. Now, but notice when you multiply this out, the constant coefficient is the product of all of those constants. So the a0 here is the product of those r's. And so I see that in another way by plugging lambda equals 0 into this whole equation. Here, it just turns into a minus 0i. This part turns into this polynomial with zeros plugged in, and with 0 plugged in for all those lambdas, I get this, which is the determinant of a is equal to the constant term here, which is the product of all of those eigenvalues. So the determinant is equal to the product of the eigenvalues. Again, the book would now have to worry about a plus or minus sign because they wouldn't know whether there's an even number or an odd number of these things, because they don't, instead of r minus lambda, they do lambda minus r, whatever. I think this is cleaner. actually, to just say the determinant of A is the product of the eigenvalues. This leads us to one theorem that I want to end with that says an n by n matrix is invertible if and only if 0 is not an eigenvalue of that matrix. Right? You can see here that if one of these r's is equal to 0, then the determinant of A must be 0, and we know that that's equivalent to being non-invertible. Likewise, if this is invertible, you can't have a 0 over here. And if it's a non-invertible, this is 0, and you have to have a 0 as one of those factors. So it's invertible if and only if 0 is not an eigenvalue, which then puts it in that long list that we've had all quarter, right, of the things that are equivalent to being an invertible matrix. Right? Just one more thing to add on to that big list of the following are equivalent. Right. So there you go, eigenvalues and determinants.